Good afternoon. So, or morning. Yes. Let's continue our morning session. The next speaker is Xinwen Zhu from Stanford University, who will talk about Tame categorical local Langlands correspondence. Please start.
Thank you very much for the. It's a great pleasure to speak in this wonderful congress. So the talk I'm gonna talk is somehow it's not the directly the report this frontier award, but all this such thing becomes possible only after the previous works. And I also should apologize for some of you because I give this kind of talks several times in different places. The slides are slowly evolving, so there will be a slight different from the previous one, but the like major parts are, people as the work is progressing, the more and more stuffs we can see. So. All right, so let's first recall the just like in the previous Marius talk, what is the class recall some kind of statement of classical local Langlands correspondence. So if we start from local non-Archimedean local field like QP or like FP double bracket T double parenthesis T, and some Langlands dual group over reducted group over F, and we can form the Langlands dual group. Where this is like the some Galois F tilde as some like field extension such that the G becomes split. Then the classical local Langlands correspondence roughly predicts a bijection between the smooth irreducible representations of this periodic locally compact group G of F and the set of Langlands parameters, which are the homomorphisms from the Wei group to the dual group up to G hat conjugation, but for G is GN, this naturality can be made precise, and in fact, this is already a theorem like for a long time. If the characteristic of F is positive, this was known in 1990s, I think, by Lamont, Rappaport, and Stuhler, and then Harris Taylor and Enya proved in the case of F is characteristic 0 around 2000. But for general group G, this is much more complicated, the story. I think some kind of thing were already, some story was already appeared in the previous talk. For example, the starting point of even the simplest situation, let's just consider the so-called unramified Iwahori block. So if you consider some very particular class of representations, periodic group, those smoothly reducible representation with Iwahori fixed vector, then what the original Kashidan-Lustig constructed, if G split, is actually just an injective map from this set to the set of parameters, which first set of parameters is before, but in this case, when it has Iwahori fixed vector, the parameter will factor through the Tame quotient, so it's trivial on the wild inertia. But there's a new component appeared in the story. It's namely, they also assign a irreducible representation of the centralizer of this parameter. So this pair appears in Marius talk as like a set of enhanced parameters. So so you see, really, if you want to have a parameterization, you need something more than just parameters. And the appearance of this rho actually, from more algebraic geometric point of view, it suggests that certain stacks should involve in the story. And namely, you can think about this rho as certain coherent sheaf on this quotient stack point modulo some group, which modulo centralized group, which you can also think about as just G hat orbit of this phi modulo G hat. Okay. So then, of course, there's a lot of development of the geometric Langlands in the last 20 years. and that the program suggests actually even in the classical local Langlands there should be some stacks involved in the story. Just namely the previous mentioned bijection of sets should be sort of lifted into some equivalence categories. So the first thing is on the spectral side, this parameter space actually do form a very nice algebraic stack. So you can consider all possible continuous representations from the Wei group to some Langlands Zhu group. Here I wrote the C of G is some C group. It's slight variant of L of G, so you can ignore that. Such stack actually just parameterize the continuous, all possible continuous representation of Wei group up to conjugation, and then it has some nice geometrical property. For example, it's a disjoint union of affine schemes modulo G hat. Each one is the local complete intersection of a nice relative dimension G hat over ZL. So I mean, when the stack itself is going to be this one modulo G hat quotient. So the relative dimension is actually 0. So there's some notion of you can make sense of continuity, which is some subtle thing, but let's ignore that. Then, as I said, we should lift the bijection of sets into equivalence categories. Then we should sort of replace the set of Langlands parameters by just the category of coherent shifts on this stack. And this is really some classical object. It's just quotient stack of some affine variety modulo G hat. So you can also, if you don't really like the stack, it's just coherent shifts on affine scheme. Just let's say spec A is just A modules, and then equipped with a G hat equivalent structure. Okay, so that's just what they should. So then you should probably naturally you expect you replace the set of smoothly irreducible representations of G of F by the derived categories of the smooth representations of G of F. But this is not quite enough. Even in a classic point of view from like the Vogan, Kotowitz, maybe a bunch of other people, you already see this is it's better to study not just the representation of G of F, but also kind of a class of inner forms. Just appeared in just like in previous talk, like the Lustig classification of unipotent representations. Really, you want to put all the inner forms all together to have a nice classification. But actually, there are some bunch of reasons you suggest. Recent years, people realize even this story might not be enough. It's part of the story, but actually this story still has some enhancement. You can study not just the G of F and its representation of G of F and its inner forms, but also kind of inner forms or its levies. You should put all of them together, and the category of representations of this huge collection of groups actually can be glued together as some category of sheaves on certain geometrical objects. This kind of geometrical object has been, and this category of sheaves has been constructed recently. So there are two approaches. One is Frank-Schulze's approach, use some Bang-G in the periodic geometry and consider like L-laddic version of L-laddic sheaves on it. And then there's another version called the nowadays called the ISOC, which is some algebraic geometrical objects, and then you can also consider some kind of L-laddic sheaves on it. And then the categorical local Langlands, roughly speaking, you predict some equivalence categories between coherent sheaves on the stack of Langlands parameters and let's say L-laddic sheaves, some version of constructible L-laddic sheaves on the stack of this ISOC, or maybe you replace this by Frank-Schulze's version. Actually, there's some, I think, hopefully forthcoming work in the summer proving this two versions are equivalent. But it's not the. This is something I'm gonna use the second version. Okay, what it is. So, but actually, there's two motivations to introduce this. One is come from the study of MAP geometry of Shimura variety, original study from Kottwitz, because this is called iso because it's sort of some moduli space of F isocrystals. So with G structures. So that appears in arithmetic geometry, but in this because this is Lie theory section, I also want to mention this iso actually really appears also in Lie theory directly. This is some kind of affine generalization. Really, naturally, the affine generalization of the linguistic theory. Namely, if you start from a reductive group over finite field, let's recall, the linguistic theory in today's reformulation, you can think about that it's a construction to construct the of irreducible representation of finite groups of D type by the following two procedures. I mean, by the following procedure, and it starts from the two observations. The first one is if you consider, you can regard this finite group as a affine group scheme, affine algebraic group over a field, and consider its classifying stack. And then the category of L-Lat shift on it is just the categorical representations of this finite group. And this doesn't really helpful because this is this classifying stack is just the geometry is too simple. It's just a point modulo some finite group. It doesn't really give you any essential new information. But then there comes from this so-called Langlands theorem, or maybe start from the Katz. So it said this classifying stack is really the algebraic group modulo its Frobenius conjugation. Here, this AUD sigma G means the conjugation of G by H, but here you twist the H by Frobenius element, and and this quotient has much more fruitful geometry, so that you can sort of see constructive representations using this more sophisticated geometrical objects. Namely, for example, you can, instead of consider G quotient of the adjoint quotient of G, you first consider G quotient of the adjoint quotient by Borel and consider this map. Then the fiber of this map is actually essentially for flag varieties, G mod B. So this has a lot of geometry. And nowadays one can reinterpret of the linguistic construction as the following. You consider certain L-Lat shifts on here. For example, you take, because G itself has some Broha stratification, which is B bi-equivalent subset. If you conjugate it by B action, so those B equivalent subsets are preserved under the conjugation. So you can just, for example, take some structure shift, some shift, constant shift on one strata, and then push forward to here. And under this interpretation, it's exactly the cohomology of the linguistic variety. What do you get? So this is so from this point of view, okay. So yes, I'm this story then will have like some natural loop or affine generalization where G is replaced by the loop group LG. But to see that, I need to introduce a little bit of notations. So I'll take O of F as a ring of integers of F, and K of F is a residue field. It's a finite field of Q elements with Frobenius. So I will take, to define the loop group, we need some disk and a puncture disk. So these are either equal characteristic. It's either like some spec of, let's see, could be, and actually we need some family versions of the disk or puncture disk. So it's for every ring R, you consider spec R double bracket T or spec R double parenthesis T, or in the mixed characteristic, when it's QP situation, you consider some version of the ring with vectors. So, and when this R is just a field, like algebraic closure of KF, with some field K, I will write this ring or this ring by L, just to simplify the notation. Okay, then because this is a ring in characteristic P, you also have some kind of Frobenius act on this. So that actually, okay. So now, then now we can define the so-called the loop group of G, loop version. So it's defined. We define it by function points. So it's R point is G evaluated on this puncture disk. So for example, when R is KF, so then this guy L is literally just the F, and so it's KF points, just like a points over finite, is this periodic group. Okay. So from this point of view, it's just like before, the finite group of D type is KF point of G. So now it's a periodic group is a KF point of some infinite dimensional algebraic geometric object. Okay, so if once you have make this following definition, you have this notion of loop group, then it's natural to generalize this the Lustick's construction by consider the Frobenius twist quotient of LG by consider the quotient of LG by its Frobenius conjugation action. Okay, and that's exactly the definition of ISOC. And then you should expect there's some so then you could have some expectation that there should be some L-lattice shifts on this stack. Then it's this L-lattice shifts here is related to the representation of a periodic group, just like the usual classical Lustick theory, and then also you might expect you should be able to construct the shifts on here via taking the push forward of shifts on this space. So just you replace Borel in a finite dimensional situation by Iwahori. So Iwahori is kind of the analog of Borel in the loop situation. So you probably could start from shifts on here, push forward, you produce shifts on this hadron quotient. That would be some analog, F1 analog of the Lustick thing. Okay, modulo all the technical difficulties, this is the case. Of course, it took a few years to really make things rigorous, but it makes sense nowadays. But even all this makes sense, there is really a major difference between finite case and the affine case. In the finite case, because in this because we have this Langlands isogenes theorem, the Frobenius conjugation action G on itself has only one orbit, and the stabilizer is a finite group of is a finite group. In the affine case, the action here on this is not just a simple, it's not just one orbit. It has a lot of orbits, and actually there's much, even on this space itself, it has more intrinsic geometric structure. So let's see that. So let's look at what's the K point. So if we want to understand this as algebraic geometrical objects, we should look at its field valued point. And its field value, just look at what are the all possible physical points on this thing. And its K points, if you think about it, just classifies G of L. L requires either K double parenthesis pi or some kind of fractional field with vectors. Okay, it's just G of L modulo this conjugation action, Frobenius conjugation action. But now the point is, this is not really just a one point set. There's also another interpretation as G torsors on this puncture disk, equipped with isomorphism of this G torsor and its Frobenius pullback. So this nowadays people call this is something like a local Stuka. And also there's if you think about it, even if you remember stabilizers, the quotient is not a set, but a group point has also automorphisms. And so one of the results or improved by Kottowitz, Rappaport, and other people says that actually this group is independent of the field K. It's meaning if you have a K map to if K is as soon as K is algebraic closed, if you have a algebraic closed field extension, this group doesn't change. And the underlying set is actually a pose set. Minimal lengths are called minimal elements are called basic. So also the stabilizer for each point here, the stabilizer under this action is defined in this. By definition, is this, and actually it is I denote by the GB of f. Actually, it is the f points of some algebraic group defined over f. So, and this algebraic group is a certain Levy. So, for example, when B is 1, you really get this G of f. But in general, you get a lot of other things. This is what I said at the beginning. Those group GB appear naturally, but not just the inner form, but meaning like even inner forms of Levy will appear. Yeah, I said the G of BF is f points of some inner form of Levy. Okay, and we regard this actually is a locally profinite group, locally compact, locally profinite group. We can regard it as just like we regard finite group as an affine algebraic group, we regard it as the in group. Okay, basic example is this is where this notation comes from. Why it's called isoc. When G is GON, like the previous group was really classifying F isocrystals of rank R. So there are actually such things are basically a vector space, n-dimensional L vector space equipped with a Frobenius linear endomorphism, and these are classified by this called the Dieudonné-Manin classification. They are given by rational numbers, simple objects are given by rational numbers, and each one has a representative given as follows. If you write lambda as R over S, you can produce some particular objects. And in this case, you see the endomorphism of simple objects is going to be a division algebra. And see if your object is, if it's an n-dimensional object, let's say direct sum of like n1 plus n2 dimensional objects, then its endomorphism will be, a direct sum of two division algebra. So that's kind of an inner form of a Levy of G1. So something like that. Okay. And this set of isomorphism classes actually also, there's a nice combinatorial way to write it as Newton polygons. It's just the convex polygons on the plane with starting from 0, 0, go to 1 blah blah something up to n something. Okay, and you make it convex. And then the partial order I mentioned before is one is bigger than another if the Newton polygon lies below the other. Okay, so therefore, because of convexity, the minimal elements are like the strict Newton polygons. Okay, yeah, this is the example of GO2. So basically, there are three situations. B is 1, you get GO2. B is if the rational number is 1/2, you get the division algebra. So it's inner form. It also could be the direct sum of two simple objects, then you get some F cross. All right. So now we can consider the geometry of it. So for every element, we can define some subset or locally closed substack, classifying those such as the underlying point is just B, and when defined this isoc less than or equal to B, meaning you take all possible underlying set with this relations, consider all possible union of all B prime less than B. So this definition a priori looks weird, but actually it's quite reasonable even in the algebraic geometry. For example, if you just consider fixed B, this is actually a strata isomorphic to the classifying stack of this periodic group. So if you have some good L-lattice shift theory, the category L-lattice shift should be the category smooth representation of this periodic group. But all these things are glued together. Actually, you have this go to here is actually finitely presented closed embedding. So this is really important, meaning if you have a, by definition, if you have a spec R mapped to it, you consider the locus of points such that the corresponding B is less than or equal to given B. That the locus is actually defined by finite many equations, okay, algebraic equations, and then J is affine open embedding. So this is usually called the Gortonic conjecture or Gortonic cuts. I don't know. This is kind of called the purity. When G is GON, this is, but there's now much general thing. When B is basic, this is actually closed because basic means minimal length element, minimal element in this poset. So there's nothing smaller. I should also mention here. Actually, one can also replace Frobenius conjugation by usual conjugation, and there's some similar geometry. Probably Shuha will say something tomorrow, maybe. So then one can talk about the shifts. I don't want to spend too much time on it, so just give a precise definition. But then to ensure this is really the definition is not that hard, but proving it has some desirable properties requires some work. But then I will assure you those properties hold. We can just work with it. So what's the definition? So we will so this adjoint quotient is some wild geometrical objects. To define the L-lattice shifts, we will first consider the usual L-lattice shifts and schemes. But we really in this world we should consider non-bounded constructible shift. This is like usual bounded constructible one. You need to really consider it, add all possible co-limits, because we are really working outside the finite type situation. If S itself is a generous quasi-compact, quasi-simple scheme, you can already, by Northern approximation, you can write it as the inverse limit of finite type thing. You just define shifts on here by pullbacks, strict pullbacks. And then for general, now this notion of a stack, a pre-stack, those are, you can think about this functors for each scheme. Just for each ring R, you get some groupoid. And the category of shifts is defined as some limit process. So a shift on the stack is, if you have a spec R map to it, you get a shift on spec R, and they are compatible with each other in a coherent way. And this pullback is using a Schrick pullback. So you always have a Schrick pullback functor, but in some cases you also have star push forward functors and the satisfying base change and projection formula. So the definition is up to here, not that difficult. I mean, modulo some techniques of taking limits and co-limits to categories, which are nowadays okay by a higher category theory, but proving certain properties requires more work. Okay, so let's not spend too much time on it. Let's just see, applied to our specific situation, you will see we really think about this ISOC as a stratified space, just stratified by B, and for each less than equal to B, we have a closed strata, and then you have some equal to B, some open inside this closed one. It's actually affine open. And then the whole theory actually works such that you can talk about shifts and push forward, pull back between the strata as if you are working with all algebraic varieties of finite type. So for example, if this is, because this is a closed embedding, you have this is closed embedding. So you have a star and the Schrick push forward, they are equal. It has have upper star pullback and upper Schrick pullback, which are left and right adjoints. Similarly, this is open, so you have this Schrick and the star push forward. They have like they are left and right adjoints of Schrick pullback, which is the same as star pullback. And then these functors induces a semi-orthogonal decomposition of this category. And I should also say, for each, according to the strata, for each strata, the category of sheaves on it is just what you expect, the category of smooth representations on the periodic group. Okay. Then also there's this category has some nice categorical properties, compact generated. The compact objects are compact when restricted to each strata, and it's zero almost outside for almost all B. Compact for each strata, this is now category of smooth representations. So compact objects are basically generated by compact induction from open compact subgroups. So in the case when lambda is FL, it's a little bit more subtle, but it's something similar. Then there's something analogous to the kind of Verdi duality in this thing. And this Verdi duality interchange the star push forward and the shrink push forward up to some shifts. And when you restrict to this Verdi duality on each strata, this is recovers this now the people call it the Brunschlin-Zivnitsky duality on the category of smooth representations. There's also some T structure out here. You can define some kind of, by gluing the T structure on each strata, you can define some kind of abelian subcategories. All right. Then with all this this kind of quick review of the precise definition of this category, now we can formulate the precise formulation of the version of categorical local Langlands, which is, in this case, I would consider rational coefficient integral is slightly more complicated, but unfortunately we need it also for applications. But anyway, so let's do rational coefficient. This formulation, I think, it's very appealing. Now it's just it's a canonical equivalence of categories without seeing all this extra complicated data. Those extra things were absorbed in this complicated defined objects. But it should set some properties. You should be compatible with parabolic induction, intertwining the duality. Here, I mentioned there's some duality here, but on the category of coherent shift, there's also this Grothendieck-Serre duality. So it should be compatible, and it also should have some normalizations and some so-called the Whittaker representation mod. So W is okay. I should assume G is quasi-split equal to pinning. This is important. Once you have that, and also fixed additive character. Once you have that, you can define the Whittaker objects representation. And it's a really representative of G of F, but the representation of G of F can be regarded as a sheaf supported under the unit. Okay, so that should actually correspond to the structure sheaf here. That's kind of some categorical and formulation of Whittaker normalization of the usual London classical local correspondence. It's not the symmetric monoid equivalence. Yes, it's not. For example, the unit is kind of dualize and shift here. It corresponds to some very complicated object, which one can see what it is, but it's more complicated. Right? Yeah. Okay. Sorry. I mean, so the unit is here. So dualize and shift correspond complex object here. Here is the unit is more just this one. It corresponds Whittaker on the trivial representation. Yeah, and of course, Frag-Schautai also has some similar conjecture with this category replaced by their version. And this conjecture in particular implies there should be because the category of vector bundles act on the coherent shift by the category of coherent shift by tensoring. That means this one should have an action on here. This was in this setup, it was not known in mixed characteristic. If F is equal characteristic, recently there's a work of Etif, Gates-Gray, genus de la fork, they also announced the construction of this action on this category when F is eco-characteristic. But Frank-Schulze, one of the main achievements of Frank-Schulze's work is actually construct this action on here. There's it. But although we don't have the spectral action, but we have some convincing evidence that this equivalence is really also the correct equivalence. So let's see the equivalence. So we will assume G is Tame ramified, quasi-split, fix a pinning as before, and also additive character. This is then inside here, actually we can define a subcategory which contains those consists of those sheaf such that when you restrict to each strata, recall when you restrict a sheaf to a strata, you can identify as this sheaf can be thought as a representation of the corresponding p-adic group. In the theory of representation of p-adic groups, there's some notion of depths. So here I write Tame, but really I mean depth 0 representation. And explicitly, this exactly means that such a representation can be obtained. It's generated, admits resolution by compacting induction of this form, where P is a parahoric of this group, and pi is a representation of the Lebesgue quotient of P. So this is also kind of appeared in the previous talk, except maybe previously it's all more restrict to the so-called unipotent representation. Because pi is essentially the representation of the Lebesgue quotient, so there's a notion of unipotent representation coming from the finite linguistic theory, and this. So then you can also define some subcategory, the unipotent subcategory inside there here. Yeah, this like the unipotent thing exactly appeared in previous Marius lecture. All right, but then the theorem says that actually the previous categorical property of this sheaf, categorical sheaves on the whole ISAC restrict to good categorical properties on this Tame, the Tame subcategory and the unipotent subcategory. It also admits semi-orthogonal decomposition, stable under duality, so on and so forth. So let's ignore that. But this theorem actually has some quite non-trivial content. It says the following: if you have B prime less than B, you know, recall this strata here is contains in the closure of the corresponding strata here. So you can start from a sheaf on here, let's say unipotent or maybe Tame. Then you do star extension and then restrict to the boundary strata, star restrict. And this theorem actually says this operation preserves the sends depth 0 representation to depth 0 representation, and sends unipotent representation to unipotent representation. So it preserves all this. It's quite non-trivial. I mean, it's very difficult to see directly from geometry, and so this makes one expect actually not just the category of representations of p-adic group admits depth filtration, but even this whole category admits some reasonable notion of depth filtration, and all this sheaf operations will preserve this depth. Okay, it's actually not really out of reach now, but let's not talk about that. So the typical objects now, after defining this, the typical objects we have is exactly this some kind of a Tame or unipotent version of the Lustig induction. So you start from sheaves. We want to construct sheaves on here by a push forward of sheaves on LG modulo the Frobenius conjugation by Iwahori. But if you want to get all depth 0, 1, you really need to pass to the pro-unipotent radical of the Iwahori. And this map to here on this like a flag quotient of LG by pro-unipotent radical of Iwahori. So this is a F analog of this the G ma U in the finite. And then so now using this we can actually even consider the deterministic induction not just a construction of single representations. Really, you can be thought as a functor from the category of kind of the monodromic shifts on this thing to here. So you start from any shift here, you pull, push, you will produce shifts on here. And the previous, like the class, in particular, if you start this is like essentially it's called the F and Hick categories. There's some like standard objects, the co-standard objects, given by Schrick extension and star extension from the like the Schubert strata. If you put a appropriate monodromy on it, and like if you this is called co-standard, this standard, and then you can do pull push. What you get is so now this is in a finite dimensional case, you do pull push, you exactly recover the cohomology or compact support cohomology of the acoustic varieties. But in the FN case, really you get the shifts on this space, not just the individual representation cohomology of individual variety. Only when you restrict to each strata B, what you recover is some kind of cohomology of FN, so FN linguistic varieties. Okay, but in general, they glued together in some very some intrinsic way and some complicated way. And it's actually not it's quite a non-trivial result actually to show these objects land in the Tame part. In fact, if you just look at the those affinite acoustic variety, sometimes it looks like it will be compact induction, not from the depth zero. I mean, like the open compact group will act on some irreducible component, not through the finite Levy quotient, but some deeper depths. That's actually possible. So a priori, you could probably get something outside of the depth zero situation, but somehow when using some like a result of Xu Hua and maybe San, actually you can deduce that this is indeed you only you don't get something outside the depth zero. But similarly on the spectral side, you can define the corresponding stack. This is much simpler. So you have the stack of Langlands parameters, the all possible continuous homomorphisms from the Wei group to the Du group up to conjugation. Then there's a Tame part which asks the homomorphism from the Wei group factor is trivial on the wild inertia. So that means the factor from the Tame inertia. And the unipotent part is you require the Tame inertia, the generator of Tame inertia mapped to a unipotent element in the Du group. So explicitly, you can write down. So up to choose some generators. These are not really fancy objects. You can really just write down very explicit. Like the Tame one is just the kind of a so-called Q commuting stack. It's basically a pair of elements satisfying this Q commuting relation. So this G is somehow like the image of inertia, and the H is somehow image of Frobenius. They must satisfy this relation. And the unipotent part is you require G to be actually a unipotent element. So I submit a little bit details. In the unipotent case, probably you need to really take the formal completion of this to have good categorical properties. But let's ignore that. Okay, and with that, or the definition given, the main theorem is indeed we have equivalence categories when you restrict to the unipotent part. So the Tame one will give you all the Tame shifts, like a depth zero shifts, will correspond to coherent shift on the stack of Tame parameter. For example, for each, let's say for each pi, and it's okay, and take which is a let's say a representation of the Levy quotient LP of this parahoric. You consider this compact induction, and then you consider this compact induction as a sheaf on here by this unit strata, then under this equivalence, it will correspond to some coherent sheaf on the stack of parameters. But by the way, this equivalence, I don't know whether I have time to see that, but it's not going to be t-exact. It would not send the honest representation to an honest coherent sheaf. In general, it will send, even like the trivial representation, will actually send the complex. It's not the coherent. But the miraculous thing is, if you do the compact induction, those coherent shifts are really honest coherent shifts. It's not going to have cohomological shifts. And it's actually so-called maximal cohomologic coherent shift. This stack itself has a lot of irreducible components. For example, the unipotent case, the irreducible components are more basically parameterized by unipotent conjugates class and some elements in the centralizer group or something like that. So there's and they intersect in a complicated way, but those coherent shifts correspond to compact induction are maximal cohomologic shifts on this. And this is actually, I don't know, for number theories, this is really consists of this, patching thing. This when you do Taylor-Weiss patching, you always get maximal cohomologic shift on the local deformation space. So this is sort of very non-trivial fact. You also have some unipotent version. This is so far for QL. For FL, actually, there's a unipotent version, and some version of this is true instead, but it cannot be true for arbitrary pi. You need some projective representation of pi, because when you for modular coefficient, the representation finite group of D type is not semi-simple. So, but if you replace arbitrary pi by some projective objects, you will still have something similar. Okay. Okay, so now what's the application? Let me give first the application. It's using this to attach classical Langlands parameter to supercuspidal representations. So for that, I assume G is semi-simple, but for simplicity, but it works for if it has connect center. In this case, recall parameter is called discrete if the centralizer is finite. Okay, so be careful. This parameter is really, although here I read Wei, but it's really this Wei times SL2 in Marius talk. Like use this Grothendieck's locomonotomy theorem continuous representation can be thought as like representing Wei group times SL2 so when this is finite, really means the full image, the centralizer of full image is finite. And it has some very nice geometrical interpretation that it's finite, the parameters discrete if and only this phi corresponds to the point on the stack parameters. And its phi is discrete if and only if this point is an open point. So this is purely stacky phenomena. In general, okay, of course, a point is open in the variety if it's a discrete point. But somehow in the stack world, the open point may not be this isolated point. You just think about A1 mod GM. It has an open point corresponding GM mod GM. Okay. One can show it may not be an isolated point. You can take its closure, and you can by analyzing the geometry of the stack, this closure itself actually is a smooth irreducible component. Actually, it's always a pre-homogeneous space modulo some reductive group. So this is some people now call this some kind of Vogan variety, some particular type of Vogan variety. And then the theorem says that for every depth 0 supercuspidal. So yeah, I should write it. It's not a F inverse. It's you consider of not just G itself, but also it's all possible. You take some B, so all possible inner forms, or maybe in this case, so-called extended inner forms. You consider this pi as a sheaf on the stack of, on ISAC and take under this categorical equivalence, you will get the coherent sheaf. First of all, it's known every supercuspidal is basically direct summand of this compact induction of something. So this really is going to be a coherent sheaf. It's not a complex of coherent sheaf. It's really honest coherent sheaf by the previous theorem. By using this, actually you know, sorry, here is pi. Here, the whole compact induction is, or maybe some direct summand is my pi in the next slide. And the whole thing, because of the previous theorem, this is really a coherent sheaf. And one can show, without knowing what it is, just by some pure geometrical reason and pure thoughts, this coherent sheaf is a vector bundle support on phi bar for some phi, for some discrete parameter. And then you can restrict this coherent sheaf to the open point. But the open point is just a point modulo the stabilizer of that representation. So then you will get the coherent sheaf will produce you a representation centralizer. And in this way, you do get attach every supercuspidal a pair, which is a phi and representation of the centralizer, the so-called enhanced Langlands parameter. Just by all this, as far as of course, I mean, as far as audience might correct me, but as far as I know, this is it was known before for this procedure is possible for arbitrary supercuspid. Of course, in many specific situations, this was known before. For example, as Mario already talked, when pi is, let's say, unipotent, there's starting from this work of Lustig, and there's a lot of when G is adjoint, but many generalizations. So there was some attachment. And in that case, it would be really nice to compare this construction and the explicit construction. I haven't done that yet. I think to identify phi is not that difficult because it's really, you just need to identify the semi-simple part. But to compare rho seems to be something I would like to talk with people to see whether this is possible. But in the other extreme case, the so-called the regular supercuspidal, which was originally studied by De Baker-Rader. So those cases, actually, I do check this construction and their construction coincide. Yeah. So and I think even like not the regular supercuspidal, yeah, there's of course there's a lot of things in between which they check, but it would be really nice. I think the unipotent part would be really the key point to check the bijection. The two construction coincide, then it would be maybe there's some way to go to other situations. All right, so how one can match objects, explicitly match objects under this equivalence. I mean, you have an equivalence, but it would not be really useful if you can say more about its property match. And so to match the objects, we will match something coming from the afferent Lustig induction provided in this construction. Meaning objects, shifts on here are meaning constructed by this afferent Lustig induction and some kind of variance. And it turns out this can be matched on the spectral side to some coherent shift obtained by what I call the so-called the spectral Lustig induction, which I will explain the why. So first of all, I would define the so-called the spectral Lustig stacks. That's really some analog of kind of analog of the Lustig construction in the spectral side. So the starting point is you have a Steinberg variety, which is a Springer resolution map to the unipotent variety, the Steinberg variety. I always consider the group version, and then you can consider the some kind of some kind of cover of some kind of proper cover of the stacked unipotent parameter. It's basically classifying the following thing. It's a unipotent parameter which is pair, a unipotent element and another element in the group satisfying this Q commuting relation, and a Borel containing that unipotent element. So this is kind of this analog, spectral set analog of this G mod B. And then you have this this map to the because the project to the second factor, which is this like Springer resolution of the unipotent variety modulo G hat, which is basically U hat mod B hat. U hat is a unipotent radical of a B hat. And then, therefore, for every representation of every character of the do group, you will get a line bound down here. On the other hand, you can look at this guy will map to the Steinberg by, because as this guy classifying this triple, basically a G, which is unipotent element, H, and the Borel containing G. Then you can conjugate the Borel by this Borel by H, you get another Borel. So you get a pair of Borel, both containing G, and that's a Steinberg. And then, because then Steinberg itself has a stratification by looking at the relative position of the two Borels. So therefore, for each W, you get the locus on here. And then, which roughly speaking, classifying those triples such that the two Borels has a relative position less than or equal to W inverse, and then there's a natural map from here to this. So this is kind of an analog of the, some kind of the Schubert cell inside. Yeah, then anyway, once you have such data, what you can do is you can start from some, you can pick some W and pick up some lambda co-character of do group, character of do group, do torus, which is co-character of torus. Then you can then produce some sheaf. Okay, this is a complicated. Then you can produce some sheaf on here, which depends on, again, the concrete formula is not that important, but it really depends on two parameters. One is lambda, which is a co-character of your original torus, and the element in the finite Weyl group. So these two combination actually is the size is the same as like the affine Weyl group. Basically, you are saying for every affine element in the affine Weyl group, you will produce some coherent sheaf, and actually that will match certain compact induction from the spectral side, from the representation theoretic side. Okay, so this is a sort of a little bit complicated. So let's see what. No, it doesn't follow from parabolic induction because I didn't prove this compatible with parabolic induction. But it's yeah, but there's some explicit way to do it. If the parabolic induction is also not that easy, more than parabolic induction. Yeah. And you can also match something not just in a, because previously when I talk about some like supercuspidal, they were never of this form, unless G itself is anisotropic. But you can also do some other thing, not just this. All right. Anyway, so some example. Example is actually you can consider some depth zero part of the Whittaker model, and that actually corresponds to the structure sheaf. And one of the corollary of this is the following. If you consider the endomorphism of the Whittaker thing, it's exactly this. Its endomorphism ring is actually commutative and it can be identified as global functions on the stack parameters. So this is pretty. I mean, there's some finite analog called the Curtis homomorphism, whatever. And also, there's another important thing is you consider the so-called coherent Springer sheaf, which is basically in the previous slides you take here. Take both W and lambda to be 1. that when W is 1 and lambda is 1, you do this, it's a coherent analog of the Springer sheaf, which the name was suggested by Benz V. And then this actually corresponds to the really compact induction from the Iwahori. And therefore, the Iwahori-Hicke algebra is realized as an endomorphism of certain coherent objects. So you can also do an unramified part would correspond to the compact induction from the G of O. There are also some, like you can also do various other things. Maybe, yeah, one more example is you analyze the G for number 3 is the GO2 situation, the unipotent stack unipotent parameter sort of from meaningless. This is some intersection of two planes with some GM action on the Steinberg component. Then you can show that actually, you can show that this famous, you consider functions or measures on P1, Steinberg is a sub-trivial representation of quotient. Actually, it will correspond to some sequence of coherent sheaf on the stack as follows. In particular, the trivial representation will live in cohomological degree 1, it's not really a coherent sheaf. It's not in the T structure. And okay, so maybe let me just say one final word is application. Another application, global application is using this, we can prove some torsion vanishing of cohomology of Shimura varieties. So in the setting of you have a Shimura variety, you have a Shimura data, you have some arithmetic variety which admits the action of the Hicke algebra in an unramified situation. And then you can consider its cohomology of compact and the compact support cohomology. And then it turns out that if the Hicke eigensystem has some generic property, the cohomology is concentrated on middle degree. So this, in the case of GON, this is proved by Caroline Schultz, which has really a lot of applications. Then there's like a limited progresses in other situations, but now everything is basically in the case of abelian type, everything is done. I should say the idea is you express the Bethe cohomology of Shimura variety in terms of coherent cohomology on this stack of local parameters and do computations there. Okay, so that's it.
Thank you. We have questions? Okay, let's send the speaker again. Sorry.
So you wrote very often things like the stack is LG mod add sigma G. So is that in that sense you're writing the stack as that's a Borel construction on the stack because the one side is an in scheme, the other side is a non-trivial stack.
So, sir, what did you?
Very often you wrote the ISOC
as LG modulo A adjoint sigma LG.
Yeah. So on one side you have non-trivial automorphism, the other side.
Every side you have a non-trivial automorphism. Yeah, the quotient is as quotient as a stack.
Not it's a stack.
It's stack quotient.
Okay.
Yeah.
Great. And one last thing. So at one point you look at the stratification and you use the J lower star, I upper star.
Yes.
Is there? Very often in geometric situations, you also have a nearby cyclospectrum by modifying. This is sort of one example of that, but is there a use of some such thing in this case?
I don't know whether there's a nearby cycle functor. Probably it will be the, if there is, probably there will be the, if let's say if this is like some codimension 1 situation is given by some divisor, locally, probably you can choose some function. Okay, I don't know. Yeah, this is a nearby cycle. Yeah, that's I don't know. But of course, you can also replace both star by Schrick. You will also have some similar thing because of duality. Yeah.
Thank you. More questions? Okay, let's send the speaker.